Hi everyone, welcome to my video series on numerical linear algebra and optimization. Today I would like to talk about matrices and their properties. So matrices and vectors are the integrated part of linear algebra and also optimization and any numerical analysis. So it's very important to have a very good grasp of these two concepts. I talked about vectors in the last couple of videos. If you have not already watched the first 5 videos, I will put a link in the description. Please definitely watch the first 2 videos to have a good grasp of vectors before watching this video. But today I would like to talk about the matrices, the properties, different concepts for matrices, and also the complexity of the calculation of some of these operation on matrices. So let's start. So what is matrix? Matrix is nothing but a rectangular array of numbers, right? So I have two matrix notation here. Usually you see in the literature the matrices are shown by the square bracket, like matrix A here, or sometimes you see that it's also shown by as like matrix B. Both of them are valid and they are used widely in the literature. A is more common than B. Now, one thing that is very important to know about matrices is the size of a matrix or dimension of a matrix. Um, Size of or dimension of matrix is the number of rows and the number of columns. Number of rows usually comes first and then number of columns, right? So the size of matrix A is 2 by 2 and B also is 2 by 2. B is exactly matrix A. I will talk about the equivalent of matrices. So this size or dimension is actually very important that usually in almost all program languages, we have a command for that. For example, in MATLAB, you have a size A to give you the number of rows and number of columns. If you issue this command, you get 2 by 2, for example. In Python, you have a shape A dot shape, for example. So A dot shape 0, for example, gives you the number of row, and A dot shape 1, it gives you the number of columns. Now, so based on, depending on the element of matrices, whether they are real or imaginary, we can define the domain of matrix differently. For example, if you look at matrix A, let's say matrix A consists of all the elements are real, right? In that case, we define the domain of matrix A as R m by n, where m is the number of rows and n is the number of columns. What this one says is that it's the domain is a set of all m by n matrices with real entries, as opposed to C m by n means that set of all m by n matrices with the complex entries, right? So what it means is that let's say for this case means that A, B, C, D, they are all member of R. They're all real values, okay? And for the other one means that A, B, C, D, they are member of the complex domain. So they can be real or they can be complex. In general, they are complex. That's what it says. Now, element of matrices are denoted by the rows and the column indices. What I mean by that, when you want to, for example, refer to a specific element, you do it like this. For example, here I have A11. You do this double subscript notation. The first one is the row, refer to the row. The second one refers to the column. Okay, so A11 means the first row and the first column. This one, the first row and the first column, right? And then A12 means the first row and the second column. First row, second column. So this is, if you want to name this is 1, 2, this is 1, 2, right? Of course, if you're familiar with low-level programming languages, they start from 0. So if you want to refer to them, for example, in program languages, you low level, you say 0, 1, 0, 1. But here, for example, mathematically, we are starting this from 1. So it's A12 usually is the first row and the second column. Like A21 means the second row and the first column. Okay. Now, one important concept is equivalent of matrices. So two matrices A and B are equivalent or equal if and only if they have the same dimension and the corresponding entries are the same. Okay, so what I mean by that is that in the above notation, this matrix A and B, they are equivalent. Why is this the case? They're equal matrices. Why is this the case? Because both of them are 2 by 2 matrices, and then corresponding entries means A11 should be equal to B11. So in general, Aij should be equal to Bij for all I and j, right? And they should have the same dimension. So let's say that when A is m by n, then B must be m by n. Okay. So otherwise, they cannot be equal if either of these two conditions is not satisfied. Now, another concept we have that is used widely in a system of linear equation, is used widely to define certain concepts for matrices, is the concept of tall, square, and wide matrices. So a square matrix is defined as a matrix that has an equal number of rows and columns. So in general, we define a matrix, let's say matrix A, to be defined by m by n. So when the matrix is square, means that m is equal to n. Number of rows and number of columns are the same. If the matrix is tall, means that the number of rows is more than number of columns. For example, what is an example of a tall matrix? The example of tall matrix is this. X1, X2, all the way to Xn. Is a vector. Is a column vector is an example of a tall matrix, or the number of columns should be more than number of rows, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So here we have 4 rows and 3 columns. This is still a tall matrix. Now we have a wide matrix. Wide matrix is a matrix that the number of rows is smaller than the number of columns. So for example, an example of that is this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is an example of a wide matrix. Okay. Now, another concept we have here is a notation for column and row of a matrix. So this is not a maybe really like a widely used notation. We usually show the column or the row of a matrix by a small letter, and the actual matrix by the capital letter. Now, so assume that we have a matrix A in general m by n, which has m rows and n columns. Then the ith row of a matrix is this. So let me just write it here. A is A11, A12, all the way to A1, n, because it has n columns, then all the way from AM1 to AMN, right? Remember, it has m rows and n columns. Now, if you are looking for ith row of this matrix, ith row is somewhere here, right? This is ith row. Now, ith row means that what we have A means that the first index is I. The second one can vary. So the first, remember, the first index is index of a row. The second one is the index of a column. So we have AI1, AI2, all the way to AI. Depends on how many columns we have. AIN, right? So like that, or if you want to show it as like a capital letter, this notation is saying like this. Doesn't matter. This is gonna be like A11 all the way to A1N, and then AM1 all the way to AMN, and the ith row is gonna be AI1, AI2, and all the way to AIN. So that's what it says. So this A means that the ith row. Now the jth column is defined similarly, so I can show it on this matrix as well. The jth column is somewhere, let's say here. This is the jth column. What does it mean? The jth column means that the second index is j, right? The jth column is the second index is j. So I'm gonna write it here. Let's just do it here again. So the second, just put the second index j, aj1, a2j, all the way to amj, right? So this is a pretty important thing to be fluent on the rows and the columns of a matrix. ith row and the jth column of matrix. Let me just write it down. Jth column. Okay. Now we get to the one of the most important concepts for matrices, which is the column and row representation of a matrix. It's very important to be familiar and also very fluent with this concept, that how we can represent a matrix as a block column vector or an block row vector. What do I mean by that? Assume we have matrix A, m by n. right? So what do I mean by matrix A? I can show the components or elements as a lowercase or the uppercase, doesn't matter. Let's say it's like this: A11, A12, all the way to A1n. So A21, let's write in the second entry as A22, all the way to A2n, and then all the way to AM1, AM2, all the way to AMN. Okay. Now, when I am talking about the block row vector, like A prime that I have here, it means that I'm gonna group the matrix as like a column wise. What do I mean by that? It means that I'm gonna consider this as one element, I'm gonna consider this as a second element, and then consider this as a nth element. So I call this one A1, I call this one A2, I call this one AN. So here in the A prime, each of these AI, I define it here, each of these AI refers to the ith, this is ith column of matrix A. How do I know that? I define it here for you. If you want to know that better, also look at the second index. The second index is the same for all the elements. A1i, okay? The first row, the ith column. A2i, the second row, the ith column, and all the way to AMI. Remember, we have m rows, and then we are choosing the ith column. Okay, so that's pretty important. You can represent matrix as this A1, A2, all the way to AN, which each AI is a column of matrix. Or if you don't want that, so this A prime is a wide, you can also say that wide representation of matrix. Wide block representation, perhaps, would be better. Representation of matrix. Now, or as a tall column matrix, you can also do the same thing, or a tall column vector, or tall column or block column vector, right? Whichever you want to call that. What is important thing is to go back to this definition. Go back to this definition, right? As a matter of fact, let's copy this one somewhere and work with a new picture here. So I want to remove all these here. Okay. So now we have B here. Let's say, again, I call it A, right? So now I want to group them as a row. What I mean by that, I will consider this one as the first element, this one as the second element, and all the way this one as a mth element, right? We have m rows. So this one will become B1, this one will become B2, all the way to Bm. That's the definition that I have here for A, right? Which each Bi is gonna be the ith row of matrix A. Ith row of matrix A. How do I know that? Look at the first index. The first index for all the entries is I. This means that this is the ith row. Okay, good. Now let's talk about the application of matrices. Matrices have a lot of application. Actually, pretty much as I said in the beginning of the video, linear algebra means matrices and vectors. So it has numerous applications in image processing and computer vision. First of all, as I talked about in the first video about the vectors, the image is a 2D matrix. Image is a 2D matrix. So image processing all about matrices. Computer vision is all about matrices, matrix manipulation, and various operation on matrices. Social network, many application of that. But for example, when you actually design an adjacency matrix for your graph, for your DAG, you use actually matrix of zeros and ones, whether they are connected. And let's say for a binary adjacency matrix, you are using the concept of matrices. And for any manipulation after that, also use an operation on the matrices as well. Graphical models, of course, for any type of graphical model, you might have, for example, let's consider like a Markov chain or hidden Markov model. For example, you have a transition matrix, you have observation matrix, and then of course you have the operation on this transition observation matrix. Then for the prior probabilities, for other probabilities, when you use a multinomial distribution, you have vectors. So graphical modeling pretty much has a lot of linear algebra and a lot of matrix operation. Perhaps the most important example for matrices are optimization and control and dynamical system. So optimization pretty much is also like a linear algebra and numerical analysis, and has a lot of matrix operations, a lot of knowledge of the matrices and their properties, and also the vectors, matrix vector operation as well. So you will see this one in a lot of application. Control as well. You have a controllability matrix. You have an observability matrix. So just a very matrix basic example I'm talking about. And the whole state space. You learn about the classical control, and then you learn about the state space, which is actually like looking at the classical control in terms of linear algebra and put everything in terms of vector and matrices. So these are just a very few examples of application of matrices that are all over the literature, all over the research and industry, actually, to be able to be familiar with these concepts. The whole linear algebra, as I said, are defined based on the matrices and the vectors operation. So now that we know that actually matrices are quite important, we need to be able to talk about some special matrices. These are the matrices that are used a lot. That's why they have a special name. One of them is a zero matrix. So zero matrix is a matrix that whose all its element is zero. So for example, 0 m by n usually is denoted by that. Is an m by n matrix, a matrix with m rows and n columns with all the entries equal to 0. So for example, here I have an example of matrix 0, 3 by 2. 3 rows, row 1, 2, 3, column 1, 2. Identity matrix is used a lot in the literature. Is a matrix, the diagonal matrix, but I haven't talked about diagonal matrix yet. So it's a matrix that elements of the main diagonal is all 1 and the off diagonal elements are all 0. But it's a square matrix. Remember the definition of a square matrix? The matrix is the number of rows and the number of columns are the same. So usually denoted by in. You can also show it by this, in by n, but when you show it by in, it's understood that the number of rows and the number of columns are the same. So I have a definition of a identity matrix here. Means that if I equal to j, means that we are on the main diagonal, we get 1. When I is not equal to j, we get 0. Okay. Now here, for example, as I said, we denoted by in, where n is the order of a matrix, number of rows or number of columns. So for example, here I have an example of I2, means it's 2 by 2, and then we have 2 ones. So it's good to know that we have n ones, for example, in in, only the element of on the main diagonal. I3 we have 3 ones, and it's defined like that. Now we have one matrix which is very similar to the zero matrix, but now all elements is equal to 1. Same as zero matrix is defined as like this: 1 m by n. For example, here I have a 1 3 by 2, means a matrix of all ones with 3 rows and 2 columns. Now another important concept is the sparse matrices. So a sparse matrix is a matrix whose all the elements is most of its elements is 0. Remember, the zero matrix was all the elements was 0. So zero matrix is the sparsest matrix you can get. But now in general, the sparse matrix is the matrix whose most of the elements are 0. Now, since they have a special application or numerous application in various literature, the concept that is very important for the sparse matrices is the number of non-zero element, or sometimes it's called the sparsity pattern for the sparse matrices. It's denoted by n and z, number of non-zero element, and the A is the matrix that we are talking about that. So n and z A means that the pattern of sparsity or number of non-zero element of matrix A. Now, for a sparse matrices, we usually want the number of non-zero element to be less than the number of rows times number of columns. What does it mean? This means the total number of elements. Total number of elements. Right? So for example, another example of a sparse matrix is the identity. And I talk about that. Let's say, for example, we talk about I4, right? We have these, and then 0 everywhere else. So for I4, the number of non-zero element is 4, and the total number of elements means 4 rows and 4 columns means 16. So it's much smaller than that, right? And in general, IN for n very large. So for example, consider I100, right? Number of non-zero element for I100, as I said, there is only 100 ones on a main diagonal is equal to 100 less than 10 to the 4. So this is definitely a sparse matrix. For a larger n, identity is definitely actually a sparse matrix. So another concept, we have a density of a matrix, which is defined as a number of non-zero element for a sparse matrix, number of non-zero element here divided by m times n, the total number of element. So it's like a usual definition of density. And for a sparse matrices, usually this should be much less than 1. That's what this says. This is much less than 1. Much less than 1. This is what we want usually in practice. So now I talk about the sparse matrix. So density of an identity matrix is what? We have n ones, n number of n non-zero elements. We don't care if it's 1 or not. We have n non-zero element. How many elements we have? N rows times n columns, which is equal to 1 over n. Okay. So zero matrix is a sparse matrix. Why is that? Because what is the number of non-zero element? 0. Number of non-zero element is 0. Everything is 0, right? And then the total number of elements is n square, let's say, or n by m in general, is equal to 0. So what about the least sparse matrix? The least sparse matrix is a matrix that it has no zero element, or we have a good example of that here, the 1 matrix. What's the density of a 1 matrix? Density of 1 m by n. So what is the number of non-zero element here? Number of non-zero element here is m by n, and then the total number of element also is m by n, which is 1. So density of the 1 matrix is 1, which is the maximum density. It's the least sparse. Let me write it down as well. So the 1 matrix is the least sparse matrix. Okay. Another special class of matrices is the diagonal matrix. So a matrix is diagonal when all the elements, all the off-diagonal elements are 0. So we don't really have any constraint on the main diagonal elements, but all the off-diagonal elements must be 0. What it means is that aij is equal to 0 if I is not equal to j. So remember, aij, when I equal to j, refers to the element of the main diagonal. So for example, if you have this example for yourself, a equal to this, what's the element on the first diagonal? A11. Then we have A22. All the way we have A and N. So the first index was the index of row, the second was the index of a column. So aij when I is equal to j, right? We mean the element on the main diagonal. So when I is equal to the j, we are in the main diagonal. When I is not equal to j, we are talking about off diagonal elements, right? So when I is not equal to j, for diagonal matrices, we get the entries to be 0, like here, like matrix A that we have here. So diagonal matrices also are sparse. What's the most important example of diagonal matrices is the identity matrix, where all this A11, A22, all the way to ANN is equal to 1. What's the density of A, let's just write A when A is n by n, when A is diagonal, same as density of the same as density of identity matrix, which is equal to n over n squared, which is equal to 1 over n. Okay, so identity is an example of as I show here, the example of a diagonal matrix. There is a notation that is used actually sometimes in different textbooks. Since the diagonal matrices only have non-zero elements on the main diagonal, usually the matrix A, if it's diagonal, is shown as follows: diag with the non-zero elements or elements that are on the main diagonal: A11, A22, and all the way to AN, right? So if you look at this matrix, we are talking about these elements because the rest of them is zero. We don't really care about them. So now, usually the identity matrix is defined according to its definition as diag of 1, 1, all the way to 1, or simply diag of 1. If you know the dimension, I can actually recover that. So these are the different notation that we have when we define diagonal matrices. Now, let's talk about the triangular matrices. So a square, first triangular matrix or a square. A square n by n matrix is upper triangular if aij is 0, if I greater than j. What do I mean by that? So I was the index of row, j was the index of a column. Let's draw this main diagonal here. Why did I draw main diagonal? The main diagonal is a set of indices where I is equal to the j. Now, anything above the main diagonal, anything above the main diagonal, here we have here one region, we have another region here. So here in this region, I is less than j. And in this region, I is greater than j. Let's go ahead with an example. I'm going to consider 3 by 3, right? So this is a main diagonal. Now here, what is this is the first row and the second column. This is the first row and the second column. I'm going to call it 1, 2, 3, 1, 2, 3, right? Remember, the first row, second column. So j, it refers to the column. So j is 2, I is 1. It's correct. Here, j is 3, I is 1. So you can see that j is greater than I here. Now here we have I is 3, j is 1. Remember, when I is 3, j is 3, we are on the main diagonal, so it's not counted. When, for example, here I is 3, j is 2. So here is a case when I is greater than j. Okay, good. Now, if aij is equal to 0, if I greater than j, where are we? Here, we are here. If this is the case, then we have a lower triangular matrix. So elements below the main diagonal is 0, right? So for lower triangular matrices, for upper triangular matrices, the elements below the main diagonal is 0. This is the, for example, upper triangular matrix. For lower triangular matrices, elements above the main diagonal is 0. See? aij is 0 when I is less than j. Refer to here. Another picture perhaps. This is the elements I equal to j. This is 0. This is where I is less than j. Remember this diagram that I had for example of 3 by 3 matrix. So if elements of above the main diagonal 0, above the main diagonal. If above the main diagonal is 0, we get this case. We get the lower triangular. If elements below the main diagonal is 0, we get upper triangular. So now diagonal matrices are both upper triangular and lower triangular matrices. What do I mean by that? So let's say A is a diagonal matrix, right? So in that case, the main element of off diagonal are all 0. This is 0. This is 0. This is 0. So it's both lower triangular and both upper triangular. That's why I define here the diagonal matrix to be both upper triangular or lower triangular. Now, if a matrix is either upper or lower triangular, we call it a triangular matrix. So here I define the matrix triangular matrix. It means that the matrix is either lower or upper triangular. So we simply call it a triangular matrix. So a couple of things. Diagonal matrices are both upper and lower triangular. And if a matrix is either upper or lower, we call it a triangular matrix. So here I want to talk about the density of triangular matrix. What was the definition of the density? So let's say density of A is number of non-zero element of A over total number of elements. Total number of elements. So what's the number of non-zero element of A for the triangular matrices? Let's talk about the case here, n by n case. So we have an n by n case and general case. We are not talking about any special case. Let's talk about a general case. So we are not considering a diagonal matrix. We are considering a general case. Let's say that the elements of here are 0 and elements of the main diagonal and below the main diagonal are not 0. They are not in general 0. Okay. You want to see how many number of non-zero element we have. We know that either lower or upper triangular matrices, they are diagonal. So we know that we have n rows and n columns. So we know that the total number of elements is n square. Okay, good. So now we have n square elements. But how many of them are 0? Easy to calculate. First, we need to see how many elements we have on the main diagonal. Because let's call this one region 1, let's call this one region 2. These two have a symmetry, right? So if we have to first subtract the number of elements on a main diagonal. The number of elements on a main diagonal is n. And then when you divide it by 2, so n squared, let me just write this step by step. So n squared minus n is the number of elements that are not on a main diagonal, right? So either in region 1 or region 2. Now n squared minus n divided by 2 are the number of elements or number of entries in region 2 or in region 1. Okay, so let's say we have number of entries in region 1. Now we have the number of entries here. We have to add the number of elements on the main diagonal as well. We have n of them. If you do that, you will get n squared plus n divided by 2, which is, I have it above, n times n plus 1 divided by 2. So we have n by n plus 1 divided by 2. Okay, so you will have n plus 1 over 2n. That's the density of a triangular matrix. Whether it's a lower triangular or upper triangular, this is considered as a density. Now, in general, triangular matrices are not considered as a sparse matrix. So I will write it down here. In general, triangular matrices are not classified as sparse. Okay, good. Now let's talk about some operation on matrices: transpose, addition, and norm. So transpose of matrix is defined by A transpose. So transpose is this T, capital T, A to the power of capital T. This capital is considered A transpose. Is defined by swapping the rows and columns of matrix, which means that if matrix A is n by n matrix, A transpose will be n by n. So in A, we have m rows and n columns. In A transpose, we have n rows and m column. What I mean by that means that when I say swapping rows and columns, I mean the element of Aij. So this is A11, A12, all the way again to A1n, A21, A22, all the way again to A2n, and then all the way to AM1, all the way to AMN. So if you, for example, consider this element, let me show you another color. If you consider this element, A21, okay? If you consider this element A21, when you write the A transpose, what I'm going to do is just swap the rows and columns. So for example, what was the first row? Was A11, A12, all the way to A1n. I'm going to write it as the first column. I'm going to write it as A11, A12, all the way to A1n. Right? What was the second row? The second row is A21. I'm going to write it as the second column. A21, A22, all the way to A2n. Right? And then all the way goes to, so how many do we have here? We used to have m rows and n columns. Now we are going to have n rows and m columns. Okay, so this is going to be what? This is going to be AM1, AM2, all the way to AMN. Okay, great.